This one should work. Good morning, everyone. It's always a morning somewhere on the internet, so I'll always say good morning. I'm absolutely thrilled to come to Taiwan. I've been spending my last 10 days in Taiwan touring the island. I really loved it. And so I'm going to talk about a lot of things tonight. Don't hesitate to grab your question at the end, and I will do my best. So today we are going to talk a bit about Kyber. Kyber is really like the next generation things we're going to do in video, and it's mostly about real-time control of machines. So let me show you. But first, like, my name is Jean-Baptiste. It's horrible to say, so JB is absolutely fine. I've been working in multimedia since 20 years. Exactly this month was 20 years. I've been, yes, working and creating the Videoland nonprofit. And I created a few companies. I created 7 or 8 companies. And yes, I was CTO of several companies. But like mostly people know me because what I've been doing on VLC and on FFmpeg. VLC is this multimedia player framework that is used by so many people, but also it's used in so many applications, right? Lots of applications are using VLC inside. But I work also on FFmpeg, which is mostly the server side that most of the video online services are using. And while FFmpeg is not part of Videoland, it's a very sister community. And we often do things together, especially like the Videoland Dev Days that we do once every year in Europe, once every year in Asia, right? Last year was in Seoul, 3 years ago was in Tokyo, and we'll continue doing that. FFmpeg is advancing quite importantly, and because like since I took over the management of FFmpeg project, we do 1 release per year, so we'll talk about that. This is important because this is a framework that everyone uses for VLC, but for other things. There is another project that is quite important, is David, right? It's the AV1 video decoder for software. It's around 30,000 lines of C and around 210,000 lines of handwritten assembly. Yes, we still write handwritten assembly for x86, for ARM, for MIPS. Yes, there are still people using MIPS, and of course, a lot on RISC-V, right? RISC-V is this open source ISA for CPUs, and this is getting more and more used. We write assembly by hand because it's faster than anything else. So you can ask, yes, it's faster than any compiler. Yes, any optimizations. Yes, we do that because we know what we know things that the compiler cannot know. And on VLC, we have around 500 million users on VLCs, and the latest things that we've shown was AI subtitles, where we basically are doing real-time live video to basically translations. So it's using some local models, right? So on device to be able to do speech to text, but also translation to translations. And yes, it does work with Taiwanese. I tested just before. There is a lot of other things in the open multimedia system. There is X264, this encoder for H264, but there is also like a Blu-ray stack, DVD stacks, and object audio called spatial audio. And object audio is getting quite important lately. To give you an idea, this was the release of FFmpeg 7 1 year ago. We did a lot of things on multi-threading. We did a lot of things on AV1 hardware decoding, right? Because most of the now GPU chips support AV1. We spend a lot of time on RISC-V and ARM optimization, of course. And we added new codecs, right? Because people don't realize, but there is new codecs on top, right? So there was EVC, there was work on VVC, of course, and that was release of FFmpeg 1 year ago. You should look at FFmpeg CLI that is now multi-threaded by the work that we've been doing, which means that you should be able to use directly FFmpeg today to do your HLS or Dash. whatever the number of resolutions, this is going to be multi-threaded. Each encoding is going to be done in parallel. FFmpeg 7.1 was the release that we did the last ones. It was a big one because we had a lot of new decoders. The first one is VVC, and that was mostly done by people from Tencent, actually, who did that and put that inside FFmpeg. But also MV-HEVC, which is a 3D HEVC extension. People seem to care about 3D again, mostly because of the Apple Vision Pro. This is the only way to get 3D video into Apple Vision Pro. XHE AEC, right, this low-level bitrate AEC extension, and IMF, right, everything related to 3D audio. And as usual, major cleanups. What's important here is that all of that is done by people worldwide, from Asia, from the US, from Europe, a lot from mainland China also. And so if you have needs on FFmpeg, please come and ask for it, because you probably have some specifics that is based on Taiwan needs. And so you should ask, and you should contribute, because everyone can contribute. On other projects, right, I spoke about David, right? This is the one where we're spending most of the time. I think we're almost finished on David, except on RISC-V. And now it's in all versions of Windows, all versions of Linux, all macOS, all iOS, and all Android versions. In all versions of the YouTube app, the Netflix app, they all use AV1. Importantly, this is an open source community. People do that on their free time, or because they are paid but by their company, and people contribute. So a lot of you should contribute too. And this is VDD in France, right? We did it in Paris. You should come to VDD in Paris, or this October in London, where we're doing VDD, or next year in Tokyo. Most of those people work because they like it, but also because it's technically challenging and interesting. So now we're going to speak about Kyber. The reasons why we need to talk about the things I talked on FFmpeg and VLC is that this is the base of Kyber. So we're seeing a lot of things changing lately, right? And we're doing, of course, a lot of drones, a lot of robots, and we're going to do a lot of things remotely to control machines. And a few years ago, everyone said, well, we don't need that. We're going to do everything on our phone, right? But then we realized that, especially with advance of AI, that you need to have access to a lot of GPU power or a lot of data in order to do decisions, right? And so maybe you're not going to be able to do everything on the device, but you need to control it from elsewhere, right? And also we've seen that, like, so far there is no autonomous cars, right? We've invested hundreds of billions of dollars in autonomous cars, and none of them have reached full autonomy. So we have the place where it can be dangerous if a drone or robot is fully autonomous, right? You need to have control. You need at some point to take control of it. Or when you're going to have AI, you probably need to have a central, like a central bee and workers bees who are going to work together. And in these cases, the control of machines from another human or another machine is key. And this is what Kyber is about. So why do we need low latency? Because you need to control machines, because machines need to control machines, but mostly because all the text that we've been doing, and we've been doing for podcasts, was about quality, right? You care about high quality of video. You care about synchronization between audio and video. You care because of subtitles and video synchronization. In this case, you don't care. When you're controlling a drone or robot, you care about fast and fastest latency possible. When you do WebRTC, right? So when you do people-to-people communication, what you care about is constant latency, right? Because if it's like that and then like that, this is weird, right? So WebRTC is done to do constant latency, but a robot doesn't care, right? robot needs fast. And that means that you care more about latency than quality. You can drop frames or degrade frames because what you want is that globally you can control. There is another thing is that most of you, how many of you plays StarCraft type video games? Right? Okay, just a few. So except those humans who are faster than normals, most of you have like around 30 milliseconds reaction time, right? Right? So your brain, yeah, 13, it goes from 13 to 70, right? And people who've been doing very intensive video games are better. That's been proven. But that means that, and today, like from your phone to a data center with 5G and fiber, you're at maybe 5 to 10 milliseconds, right? So going back to the data center and back is around 30 milliseconds, right? So now your latency will depend on your local processing, right? So local processing is important now because you could do things at 40 milliseconds, even going to a data center. So that's why we care about low latency. So at the beginning, when we did like adaptive streaming, right, normal HLS or Dash, right, we were at 60 milliseconds, and we came to low latency, right, it was 10 milliseconds, and then ultra low latency, order of 1.1 seconds. Then, of course, mega ultra low latency, WebRTC, right, 100 milliseconds. And this is the key. But the question is, can we go faster? And the goal here is 10 milliseconds, right? So that means the local processing, encoding, and decoding time is around 10 milliseconds. Of course, we're talking about encoding, right? It's normal encoding latency, right? If you've been in broadcast or mostly in production, we talk about lines of latency, right? In SDI, we talk about 16 lines and so on. Here, we're talking about going over the internet. And 10 milliseconds is the goal, because 10 milliseconds plus 30 makes 40 milliseconds end-to-end latency. And that, for most normal humans, they don't see the difference, except if they play good video games. And there is so many use cases, right? Autonomous cars, autonomous drones, submarines, autonomous rovers, industrial robots, right? Just to do supervision, right? Because, of course, all the factories are now full of robotics, right? But you need someone to supervise it, right? But also a lot of things on surgery and also VR and AR. But you can control a machine or you control a virtual machine, right? And it goes to software, right? So that's remote desktop, 3D and VR rendering in the cloud, AI avatars, right? Virtual robots, things that are going to think, and you need to feed a machine learning model and it's going to react real time. And in all those cases, it's always the same thing, right? You have 1 or 2 or 3 video feeds that need to be the highest quality, but also the lowest latency possible. And you have bidirectional control. And all that needs to be together. So what is Kyber? Kyber is an open source SDK based on VLC and FFmpeg, who's doing the lowest latency possible based on Quick. We'll talk about that. It's streaming with normal codecs, right? Nothing specific. It supports multiple codecs. It predicts some network degradation in order to know when the networking is going bad. It has some video sampling, super sampling. It's based on VLC and FFmpeg, which means that it works everywhere and it's quite flexible. So how does it work? Is that you have a server, where it's a drone, a machine, a headset, and so on, who's going to send 1 or 2 or 3 or 4 video streams, right? Audio and video. But all of those needs to be synchronized. It's very important for a robot, right? Because when you're going to have a humanoid robot, it's going to have 5 to 10 cameras. And stream that in a coherent fashion over one single socket, right? Compared to WebRTC, compared to RTP, GeForce Now, and so on. This goes over a single quick socket, and then you have bidirectional inputs to control the machines. And because it's based on VLC and FFmpeg, it runs everywhere. So maybe a demo. So let's see if I can launch the demo. So what you see on the right, oops, no. Okay, so what you see on the right side is the actual game playing, right? And what you see on the left is actually the video of. So this is the same machines. They're working exactly the same way. Same graphic card, same Asus screen, but one is a game, the other is not the game. And the inputs go on the other direction, right? So that goes directly to the machine and the stream. This is, of course, a local network, right, with 0.05 milliseconds of latency, but this is it. So now this is the same, except it's running on Mac Mini, that is in the middle. And of course, Counter-Strike is a good test. This is on Linux, of course. Elden Ring doesn't run Linux. I wish it had, but unlikely. If you see when the camera rotates, you see the artifacts. But of course, it works with mobiles. So you have your Bluetooth control directly on the machine. Then the controls are sent to the server and back. And this one is interesting because it's Street Fighter 6, but mostly it was inside Chrome, right? So there is nothing to install. It runs with normal HTTP3 web transport control without any changes. And this is important because most of the real-mode control protocols have been completely proprietary, and we have better quality. So this is, of course, a Linux. It works with a Linux server, of course. Yeah, and so it took us a year to get to 16 milliseconds glass-to-glass latency. So glass-to-glass is that you take a picture, you put the two right next to each other, and you take a picture with a high-speed camera, and you have like a red dot that moves on each frame one-to-one, and then you count the difference. So we arrive at 16 milliseconds. 16 was good, right? But when you are 16, you don't know if you're limited by the encoding time and the decoding time, or by the screen refresh rate, right? So that's why we bought the Asus monitors, right? So we moved to 120 hertz, and then we measured a frame and a half, right? So I have 12 milliseconds. But I was also the same question, like, are we good? No. So we put it at 240 hertz, and that's where we see 8 milliseconds glass-to-glass latency. Can we do better than that? Probably no. I'll explain later. If you do on the web, it's mostly the same. You add one extra frame of latency because you have the Windows compositor and the Chrome compositor, right? So that's 2 frames. It adds an extra frame. It's even better because we can do negative latency. Okay, so here we're going to do negative latency, right? So the same servers and client, except at some point, yes, here, oops. Oh. So you see the frame here is in advance compared to that one. How is that possible?
Do you mean the rendering takes longer time than video transfer plus video display?
Yes, that is correct. So what is happening here, because of course I did not break the law of physics, I wish, but no. So what is happening here is that we put the server, it's still in the screen here is still at 60 hertz. And this one is 240 hertz. But so that means that in the 16 milliseconds of refresh rate of the servers, we're able to grab the screen, encode, go on the network, go on the other side, decode, wait for the next vsync, right? Which means that we've done that in less than 12 milliseconds, right? Because if that means every 4 frame, you're in advance, right? So you arrive really at the point where, oh, you're toying with the right level, right? No. Sorry, this doesn't like too much. So Kyber is open source, it's real time, control of machine, and SDK. Works on client server. It has a client, the server, and the networking stack. It streams video, audio, subtitles, and the inputs. It's based on Quick, and as you've seen, it's multiple platform for the client and the server. It works with all codecs and all hardware encoders, and it's based on VLC and FFmpeg. To get a bit more inside features, what happens is that we wrote a video server which is focused on being push frames, right? So we are pushing frames because FFmpeg and VLC and GStreamer and all you're using has been being pulled nonstop in order to add buffers. But here, in order to remove all the buffers, everything is like doing push, right? So it's a graph-based, real-time GPU compositor framework that we've been developing based on TXProto. Guess what? For the inputs, it's exactly the same. We've written a new input servers, written in Rust, of course, that is doing a graph-based real-time push protocols. And everything, of course, is timed so that audio, subtitles, video, and inputs are timed with the same timestamps. The server side can do overlays, and the player side is VLC modified to have no buffers. We've tested with H.264, HEVC, AV1, VP9, LCVC, audio is PCM, FLAC, Opus, and so on. There is no limitations because it's really like agnostic. Everything that goes into MPEG-TS can basically go over Kyber. And most of the time we stream in 420 because that's what most of the decoders support. And what we do is we have a small machine learning upsampling model which does 420 to 444 upscaling on the client side, right? So that when the client side doesn't support 444, you can reproduce a bit. And so you avoid those very horrible red artifacts that you see when you're streaming some video game content, for example. The inputs stack, as you said, it works exactly the same. It's written in Rust, though. It's not based on VLC. It supports keyboard, mouse, copy-paste, gamepad, file transfer, USB over IP. So you can plug a Wacom tablet and unplug it the other side. And networking, we'll talk about that soon. What's important also is that we can do desktop streaming, app streaming, and pixel streaming. And what we do is what we call sensor fusion, is that we can take all the inputs and all the videos, give me a second. All the video feeds can go together. We retimestamp them with a common clock because, of course, real-time audio cameras, the clocks are drifting. So we rebase that on a single one so that we can basically ship that. So the protocol is based on Quick. Quick is a UDP-based TCP-Lite protocol that is the base of HTTP3. And so we take basically the low level of HTTP3 where we send some our packets, and we'll see how we do that. No. No. Yeah, I have the screen has disappeared. Oh no, it's okay. So what happens is the audio video server is based on TXProto, right? So that's the video server. On the other side, it's a VLC player. The input servers on the server side and the input servers on the client. There is no client on the inputs because all inputs are bidirectional. Basically, except your keyboards, all of them are bidirectional, whether it's USB or mouse and so on. And then you mux that on a single socket so that you can have like multiple sources, multiple audio, videos, and so on. And they go all mux into a single socket, so then they can be sent. The web version is interesting because we do Rust. Everything is compiled directly in WASM, WebAssembly. We don't use Quick, but we use web transport to be compatible. And the decoding is done with web codec. and the decoder is VLC WASM. So we don't use any WebRTC. So the network protocol is also, so we use QUIC, and inside QUIC, we do all the video, all the inputs are reliable, right? So there is retransmission when it's dropped, like a normal HTTP3 sockets. But audio and video are using datagrams, right? So they can be lost, like UDP. And in order to not destroy too much, what we do is we use forward error correction to rebuild the packets on the client side. So we're going to over-transmit maybe 5%, 10%, and then we're going to have network degradation, but that's okay because we will be able to rebuild the packets, right? So the audio, and this depends on how much entropy there is. And so all the forward error correction is computed on all the video feeds together, right? So that you increase the bandwidth. And also one of the main advantages of Kyber is that since everything is on one single stream, you can do bandwidth adaptation on all of them at the same time because you compute at the transport level and not on each of the video like you would do for adaptive streaming. And because when you're going to control a drone or robot, you're going to have multiple video feeds together, this is very important. So yeah, as I explained, right, so either you have streams which are reliable or datagram which are unreliable. Forward error correction, what we do is that we align the forward error correction on the video packets and we match the Ethernet MTU so that we avoid fragmentation, right? So the FEC is going to be on multiple video packets or audio packets from all the video streams. So you have more or less understood everything I said, of course. Now I'm going to answer why we can't go under 8 milliseconds. The green part you see is basically the encoding time of the, we are talking 1080p, 60 FPS with the GeForce 1080 doing encoding with hardware NVENC in H.264. And you see that the decoding time is around 2.5 milliseconds, right? So when you take green plus orange, you arrive at what you see here around 6 milliseconds, right? And if you take the P99 right here and here, you arrive at around 8 milliseconds, right? So in order to go lower, you need to have a faster encoder. And so NVIDIA needs to be faster. And yeah, and that's mostly how it works. We have time for questions. I answer every question, as Drake says, like there is no taboo, so don't hesitate.